Good morning.
Good morning. How is everyone?
I'm all right. Oh,
Ready for more learning today, Amy?
absolutely.
Absolutely. Excellent. Hey, Tyler, how's it going? Yeah.
Good.
Hey, I got a tooth, everybody. No more retainer and no more empty space and no more lisping. I finally got my tooth. I'm so excited. I got it yesterday afternoon, or maybe it was the day before that. I can't remember. Yeah, it was right after your class on the day before that. That's what it was, Tuesday. So life is good. I'm with teeth will travel. Last time we were working on chapter 13. Let me just double check something. Make sure we're all on the same page as far as what's to be done, what's being done, that sort of stuff. We got about halfway through chapter 13. I had mentioned Spectra, the Obia Fine Girl Kiss Me. I'd even mentioned about, excuse me, Pickering's harem, as they were sort of sexistly called. But they were also called the harder computers. So we'll talk about that a little bit more. It looks like, far as tests go, chapters 9 and 10 practice test, which is practice test 5, that's actually open. Our last test is currently still open. That's chapters 9 and 10. So that's due on the 19th, which is 4 days from now. So that should be Sunday. I'm going to go ahead and open test 6 as well, which will be on 11 and 12. So that'll be open. I'm going to make that due Thursday or due Wednesday night at 11:59 p.m. So actually, no, I'll go ahead and open up practice test 6. That's it. And then probably Thursday of next week is when I'll open the next test. Any questions on that? All right, I'm putting up the practice test right now. Let me see. 11 and 12 is one I want. That's practice test 6. It has now been added. Let me make sure it works properly. Looks like the questions are all there. That's good. And yeah, so practice test 6 is now up. You should be able to do that. I'm going to go ahead and moderate it, which means those of you who have accommodations will actually get extra time to do it, of course. Let me see. This test 6 right here. Does anyone have any questions while I'm just going through my tasks? It looks like I'm trying to remember the people that have accommodations. Actually, I have a little file that straight on that. Another person just came in. That's helpful. Okay, so moving up here, moving down here. Sorry for the delay, everyone, but I actually gives students more time to get in, so that helps me a little bit. Oh, we're in 131. Yes. Okay, so now recall who has accommodations. They're all double. So don't. One down, two to go. Two down, one to go. And all three are now done. All right, so I've got everything up to date. So what I'm reminding you is you have a test that's due on the 19th. That's test 5. Practice test 6 has already been put up. We're actually covering chapter 13 right now. So the fact that we're testing by Sunday night on chapters 9 and 10 is, shows you that you obviously are behind a little bit on tests. So I'm probably going to open up the test. I might actually open it up Tuesday, but if not, I'll open it up Thursday. Uh, and you'll have at least a couple days. I usually like to do it over a weekend, but sometimes times get tough. So I might even do it where it's open Tuesday. You have until Saturday midnight to do it, but that would allow me, the following Thursday to open up yet another. So that's what I'm leaning towards. Uh, anyway, so make sure you don't miss your test, which is due on the 19th. That's test 5 on chapters 9 and 10. The practice test has been up a long time. And go ahead and start doing your practice test 6 for 11 and 12. Uh, excuse me. After we finish chapter 13, I believe we go to 14, and that's about it. Once we didn't, let me double check that with our textbook again. It's a weird scenario that we're doing because we had 131 and 132 have so much overlap. I always got to double check, make sure I'm not misstating something. So yeah, once we go, yeah, that's right. We go from 13, which is basically measuring the stars, and then we go to 14, which is about our sun, and then after that we'll go to 24. So we have lab today at 1:30. It'll be a very brief lab. I've got another activity for you guys to take on yourself. So if you just show up at that time, then you'll be counted as present, and you'll see the documents actually in week 13 that you have to work on. If you don't show up, it's not that big a deal. Of course, you always miss points for missing class, but I'm not doing a great deal of explanation. I'm just more or less allowing you to do a lab. But I'm working it down between 1 or 2 labs, one of which is doing some discovery on specific constellations. The other one is something from the Learning Astronomy by Doing Astronomy manual. So I haven't decided which one I'm going to do yet, but both of them are pretty self-contained. And it looks like no one has any questions, so I'll go ahead and jump right back into chapter 13. Still no questions? Okay. So when we last spoke, we were actually on the slide that's after this, which is, you can see right here, that spectral types 1. I went back and made a predecessor instead of relabeling all of them. I called that spectral type 0 because I wanted to add something to it that you really should get to see. So I'm going to go ahead now and turn this to full screen. And I want to introduce you to Edward Pickering's harem, which I think in some sense the more polite and respectful term would be the Harvard computers. So Edward Pickering ran the Harvard astronomy, basically the astronomy lab, the observatory and all that good stuff. And he was head of the department and all that cool stuff. But one day he was complaining about one of his grad students saying that he was an idiot. And as I told you before, he actually said, my housekeeper could, turn that hate yarn. He said, my housekeeper could do a better job. And then poor salt on the wound, he brought his housekeeper in like the next day or the next week or something. Anyways, I made a mistake. I think I mentioned that the housekeeper was Annie Jump Cannon. That's not correct. Actually, Wilhelmina Fleming was in fact the first one. So she was the housekeeper that Edward Pickering brought in. Later, we had Annie Winlock and 3 other women, and then it ultimately became the people you see listed here: Wilhelmina Fleming, Annie Jump Cannon. Annie Jump Cannon actually classified over 250,000 stars all by herself. Annie Winlock did quite a few. Henrietta Swan Leavitt is responsible for the discovery of variable stars, Cepheid variables. Antonia Mari and Florence Cushman did some other things. I would recommend you guys look straight at the Wikipedia page and just do a wiki search for Pickering's harem or even Harvard computers, and you'll find the wiki page. You'll find this photo, which, by the way, if you click on the PowerPoint, you'll see it actually has the attribution to it. But it's really cool to think, here we are in the late 1800s, early 1900s, and we've got women kicking butt in astronomy. Henrietta Swan Leavitt gave us the curve about Cepheid variables. that allowed Hubble to measure the distance to the Andromeda Galaxy. Uh, if I remember correctly, Annie Jump Cannon actually, let me stop that for a second. Annie Jump Cannon had actually, dang it, she had actually made quite a few other discoveries as well. Her other discoveries included, if I remember correctly, the Horsehead Nebula. I'm pulling that open now to make sure I'm not giving you a line of crap because I forget all these women and all the wonderful things they did. I forget which ones did which, for instance. Not that I forgot them. So Annie Jump Cannon is largely credited with the "Oh Be a Fine Girl, Kiss Me." Cecilia Payne, who wasn't technically part of the harem, at least initially, or excuse me, part of the computers, but later on she does work with them, and she actually explains what the "Oh Be a Fine Girl, Kiss Me" uh, spectral classification is. Antonia Mari, she found a star that star size related to the actual spectra. So she could look at a spectra and then use that spectra to determine whether the star was large or small. Henrietta Swan Leavitt, like I said, did the Cepheid variables. Wilhelmina Fleming, that was the maid. She published the first basically discovery of a white dwarf, 40 Eridani, which means it's the among the 40th brightest. I think it is the 40th brightest star in Eridanus. In 1907, she published 222 variable stars she had found. She also discovered the Horsehead Nebula, which is now in the International Catalog as item 434. That's in the Great Orion Nebula, by the way. It's just a little bit below Alnitak, which is the leftmost belt star in Orion. She actually came up with the original idea. This is again Wilhelmina Fleming, the maid. She came up with the original idea of using A, B, C, D to classify stars. And what her motivation was that A had the most hydrogen. A B type star seemed to have a little bit less hydrogen than A's. C stars would have less hydrogen than B. And that was the way it all started off with, is just A, B, C. And they went all the way through. Ultimately, we switched that around and made it the modern system. And under the modern system, that's what we got to throw away everything but O, B, A, F, G, K, and M because of the Annie Jump Cannon, and Cecilia Payne showed it was actually the temperatures. So that's kind of cool. Florence Cushman, she actually published a 1918 version of the Henry Draper catalog, and for that one, she was in the publication, but she did all the positions and magnitudes of all those stars. So all of these women did really monumental work. They were working under another woman, by the way, Miss Draper, for which the Henry Draper catalog is named. She's the spouse, or actually the widow of Henry Draper, and she was the one that basically gave millions of dollars to Harvard to actually make a catalog of stars of all the photographs they had taken. So between her and the Harvard computers, women really kicked butt in the astronomy world. So I like to point that out. You know, someone that has two daughters and who actually both of which like science, but just didn't have that many people to cling on to as role models as female scientists. Obviously, they've had more than future past generations, but and less than future generations will have. But anyway, she's it's good to mention that. So I recommend you guys checking this out. There's also if you just do a search for Harvard computers or Pickering's harem, you'll find all sorts of stuff. There was a Science Friday program where they talked about sort of the biographies of all these women. I definitely recommend you check those out. So here's the ultimate classification. As I said, we started with A having the most hydrogen lines. And if you look right here, see these dark, dark lines, those are the hydrogen. Notice they're a little less dark the lower you go, and they're less dark the higher you go too. And that's because the A stars actually have the largest amount of hydrogen. The B stars have the second largest. The C stars would have the third. The D stars would have the fourth. E would be the fifth. F would be the sixth, and you can see by the time you get to the F stars, you can still see the hydrogen lines, but they're not all that clear. G, again, you can barely start to see them because that's even less hydrogen. H is no longer part of it. I is no longer part of it. J is no longer part of it. K is now part of it. And you can just barely make out a little bit of a hydrogen line here and here and maybe a little bit here in K star. So that was what it started off as. Now we have OBAFGKM, and I told you the mnemonic I use is "Oh be a fine girl, kiss me." You can make up your own. In fact, when you make up your own mnemonics, they tend to stick better. So by all means, make one up. The sun, by the way, in this classification is a G2V, as in the fifth letter of the Roman numerals. Okay, so what they did was they found out the O stars, B stars, A stars, F stars, G stars case. Just saying that was too large of a temperature range. So they ended up dividing up the O stars into O0, which were the hottest of the O stars, to O9, which was the least hottest of the O stars, O5 being roughly in the middle. And you can see, for instance, the O5 star is 44,500 kelvins. Then you'd have B0 stars would be the hottest, all the way down to B9, which is the coldest of the B stars. You can see the B0 is 30,000 Kelvin, whereas the B5 is 15,400 Kelvin. So I do expect you to know that O is the hottest, M is the coldest, and I expect you to know which is hotter, O9 or B0, that kind of thing. But other than that, I don't need you memorizing all these temperatures and stuff like that. So you just need to know that sequence. And you also should know, obviously, as an educated person living near our sun, you should know that it's a G2V star. The G2 means it's classification G. The 2 means it's around 5,860 Kelvin. And then the V means it's a main sequence star. So they have a Roman numeral 1, a Roman numeral 2, a Roman numeral 3, a Roman numeral 4, and then Roman numeral 5 is the main sequence star on the Hertzsprung-Russell diagram. And then they have a WD, which means white dwarf. And the 1s, the 2s, and 3s are like giants, red giants, super giants, subgiants, all that kind of stuff. So the hot ionized hydrogen loses its electrons and therefore creates no absorption lines. That's where I was telling you, you can use Wien's law to actually determine the temperature of a star by making that plot that looks like this and then has a peak and then gradually falls down, finding the wavelength of that peak, using that in Wien's law gives it to you. But as I told you, those curves often look like crap. They got a lot of jigs and jags in them. So it's a little hard to find the peak, but you can narrow it down even better by saying, okay, well, I know hydrogen has a buttload of lines when the star is in the range of 9,520. In fact, I think it goes down, I want to say from 5,000 to 10,000 is the range. It might be, yeah, 5,000 to 10,000 sounds about right. That's the sweet spot, if you will, for hydrogen. So if you see really intense hydrogen lines, you can immediately say, okay, well, it's somewhere between 5,000 and 10,000. And then you say, okay, well, let's look at these lines. Well, these lines are, let's say, I'm just making up stuff now, so don't hold me on what I'm talking about. But for instance, they might say these lines are from nitrous oxide or something. Well, they have a range, instead of 5,000 to 10,000, their range is 9,000 to 15,000. Well, since both of them are in there, that's whittled our range down from 9,000 to 10,000. So down to 9,000 to 10,000. So we've already honed in on 1,000 degrees in which it must fall. So it's got to be no bit lower than 9,000 and no higher than 10,000. Then you can find another element, and hopefully that one will narrow it down to between, something and something else that's actually smaller than 1,000, i.e., 10,000 minus 9,000. And slowly you get a much more accurate temperature scale. Okay, that's how modern astronomers can do a better job at determining temperature. The coolest stars have absorption lines by heavy elements and even molecules. So the M-type stars, you will actually get, like I was talking about earlier, nitrous oxide or titanium oxide or various other molecules, in addition to H2, N2, stuff like that. Of course, H2 is molecular hydrogen, but the fact that their temperature is so low means that they're not colliding so frequently. So there's a chance that the individual atoms still hold on to their electrons. What's worse is or what's even more important is that their molecules are staying together as molecules instead of being hit so rapidly that the molecules break apart into individual elements. So that's what's going on in the M-type stars. As you can see, the hydrogen lines fade or disappear when there's too little energy to get electrons to higher level. So that's why I said the bottom levels like 5,000. What we find is if you get below 5,000 Kelvin, then basically the electron in the hydrogen atom is staying at its lowest level, and any collisions usually are not enough velocity to actually bump it up. And the reason why it's not enough velocity is on average, the temperature is 5,000 Kelvin or bigger, of course, but 5,000 being the lowest one. At 5,000 Kelvin, when you go lower than that, that means the speed of the individual atoms and molecules going around is low, and there's literally not enough energy to break apart even the electron to bring it up from one orbital to another. So that's why you get almost no hydrogen lines below 5,000. And then if you go above 10,000, then it's so energetic that the hydrogen's been ran into several times, and it's almost no likelihood of finding any electrons left in the hydrogen atom. So you just got a proton going around with no electrons. That is another reason why these lines disappear as you go up. So as you go higher and higher temperatures, the lines get less prevalent, and as you go lower and lower temperatures, they get less prevalent for, like I said, somewhat opposite reasons. Temperature, like I said, in Means law is also measured by color or color index. Stars with a higher proportion of red in their spectrum are cooler, and stars with more blue light are hotter. The hottest stars have weak absorption line hydrogen. So you're looking at the O stars, those lines are quite weak, and an O0 star would be even hotter, on the order of 50 some Kelvin, 50,000 Kelvin or so. And hydrogen, and helium. So you find very weak absorption lines of hydrogen and helium in the hottest of the hot stars because, like I said, it's so easy to kick an electron out of a hydrogen or helium atom. Once they're gone, there's very low likelihood that they're going to be falling back in there and then making a transition from one orbital to the next. And remember, that's what these lines indicate. They indicate, in this case, energy was stolen from the core. So energy is coming out of the core of a star, and it goes through a lower density, cooler gas, namely the atmosphere. And that lower density, cooler gas will only steal photons that it can use. So it looks for photons, calculates the energy of that photon in some sense. I'm giving it some prescience here that it doesn't really have. But basically, it sort of compares that energy to the energy difference of every pair of orbitals it has. If it happens to have a pair of orbitals with exactly the same energy, then that photon will disappear, and in its place, an electron will switch from a low orbit to a high orbit. That's what these things are. But if you've hit your atom so hard that there's no electrons left, then you're not going to get very many electrons jumping from a low level to a high level because there's not that many to begin with. So that's what we're talking about here. Medium stars have strong hydrogen absorption lines. So they're calling medium stars obviously A, and that's why I gave you the historical context that they originally started with A being the most hydrogen, B being the second most, and stuff like that. And later they figured out a temperature scale was better used. I already told you about the heavy elements and molecules being in the M-type stars. When you look at stellar compositions, generally speaking, all stars sort of match what our sun have. But these things down here beyond the hydrogen and helium, they differ quite a bit. So if it was a first generation star, for instance, that means a star that was born of a nebula that was not a result of a previous star dying, okay, then all those stars that were born that way are called first generation stars. And we'd expect them to only have hydrogen, helium, and maybe trace amounts of lithium, beryllium, and boron, because those are the only things that were made by the Big Bang. But the vast majority of which is obviously hydrogen, helium. So if you have a first generation star, you expect to have just basically these two, and maybe way down here at the 0.00001 mark, you might have uh, beryllium and stuff like that, lithium and boron. Second generation stars, of course, have the advantage of having the first generation stars died, many of which were very, very large and therefore went supernova. So they created a lot of these elements, including iron. So second generation stars can have that. And this shows, this being the composition of our sun, shows that it's got iron in it. So it must, in fact, be at least a second generation star. But excuse me, given its age being 4.5, 4. Yeah, roughly 4.5 billion years old. We know that was some 9 billion years after the Big Bang. So we know it's certainly way later than a second generation star. But the big thing is when we're actually looking at the stars, now that we've measured, I've showed you the way we can measure distance and use that ladder. Now we're starting to classify various stars and identify their properties. And the properties that they have, like I said, are things like what elements are there, what their temperature is, what their radius is, what their luminosity is. And remember, brightness is more a function of distance. So it's really luminosity that matters, how much total radiation they're putting out. And that, according to the Stefan Boltzmann law, depends on the surface area, which goes like r squared, and depends on the temperature, which goes like t to the fourth. So those are critical criteria. And ultimately, what we discover is mass is really the one thing that tells you how all that's going to end. So if you know what the mass of a star is going to be, then you can predict its lifetime. You can probably predict its temperature pretty well. You can predict its radius pretty well, at least up in the what we call the main sequence area, which we'll talk about. Okay. It turns out the sizes of stars, well, even through the best telescope, when you look at a star, it's essentially a point. That's why when I showed you the Hubble Deep Field and various other deep sky photos, I said anything with a little cross over it. Excuse me, anything with a little crossover, it's a star. And that's because the star is so much like a pinpoint that the individual light coming from it diffracts off of the parts of the telescope that hold the mirrors in place. So you're getting those little crosses from parts of the telescope, and the fact that the star is actually a point object. In other words, it's infinitesimally small. You can't actually see the physical dimension of it with even the best telescopes. What you can see, though, oddly enough, is we can see Betelgeuse because it's so big. We can just recently we started to get to a point where we can actually see a little bit of the actual size of Betelgeuse, but that was for a long time. All stars were pinpoints. But some of the closest stars with some of the best telescopes, we can start to see a little bit of disk. At least that was the last I read, I think around 7 years ago. It turns out once you look at the stars, you obviously even if you do see it as a something other than a point object, the fact that it's barely other than a point object tells you that your drawing or your picture is not going to be a good representation of the size. In other words, you're not going to be able to measure it on the thing with any kind of precision. So what we end up using is the Stefan Boltzmann law. Once we figure out the temperature. Once we figure out the temperature and the actual brightness, which, like I said, brightness is always easy to do for modern astronomy. You just have to basically take the total number of photons that are hitting your CCD or your camera per unit time, and that'll give you the brightness because you just take that energy and divide it by the square, or excuse me, the area of the actual CCD. Once you have that, if you also add the distance away, then you know the luminosity. Once you add the luminosity and the temperature, then you can automatically figure out the radius because luminosity is essentially some constants times r squared times t to the fourth. Since you have t and luminosity, you can obviously get the r. Turns out there are many more small stars than large ones. When we do the Hertzsprung-Russell diagram, you actually see the ranges of sizes. But they're on the order of maybe, if I remember correctly, about 1,000th the radius of our sun, up to I think around 10,000 to 100,000 times the radius of our sun. how do we actually determine the masses? Well, that's a little bit more complicated. But just like our Earth, we can use our Earth to our Earth's orbit around the sun to figure out the mass of the sun, or we can use the let's say the orbit of the moon to calculate the mass of the Earth. So when you have a small object orbiting a big object, you can automatically get it by just using Kepler's third law the way Newton wrote it. Because Kepler's third law has like p squared over a cubed is equal to some number. That number depends on the gravitational constant, and it depends on the mass of technically the two stars, the sum of the masses of the two things. So that could be a star and a planet, or two stars orbiting one another. If you're lucky enough to find that one is literally, 1,000 times heavier than the other or more, then you can just ignore that and just solve for the bigger one. And that's what we do, for instance, when we're talking about the a planet orbiting our sun, because even the largest planet, Jupiter, is less than 0.1% of the mass of our sun. Now, if you are looking at stars, it turns out that generally stars come in groups more so than lone stars like ours. They even have, a lot of them have like planetary star systems set up as well. So there's almost always something orbiting a star, bare minimum. And in fact, the vast majority are multiple stars. So if you say, for instance, find a binary star system like this one, you've got this you've got this built-in way to actually determine the mass. So what you know is that when two stars are comparable in size, and it's actually true all the time. For instance, our Earth orbits the center of mass of the Earth-Moon system just like the Moon does, and the center of mass of the Earth-Moon system is not, I repeat, is not the center of the Earth. It turns out when you calculate the center of mass of the Earth Moon system, the center of mass is about 7/8 of the way from the center of the Earth out to the outside edge. So if this were actually spherical and this was a spherical representation of the Earth, that spot is a pretty close estimate of roughly where the center of mass of the Earth Moon system is. And that is the point that actually follows an elliptical orbit around our sun. It's not the center of the moon, and it's not our center of the Earth in this case, nor is it the center of the moon. It is that little spot within the Earth. And then, of course, the moon is going around it like this, and the sun or the Earth is going around it with much smaller circles. So the way everything works is things orbit around the common center of mass. And in order for that to work out, you have to have the objects on opposite sides of the center of mass at all times. So when star one is to the left of the center of mass, star two must be exactly to the right along a straight line that goes through the center of mass and the two centers of the planets, or stars in this case. By doing that, you realize, okay, well, when the star A or star one is here, then star two must be there. And then when star one is here, star two must be there. And then when star one is here, star two must be here. And then finally, when star one's back to here, star two will be there. So what you see from that is clearly when you have two stars orbiting the same center of mass, then they both have the same period. So Kepler's law, which relates the period to the semi-major axis, has a set period for both of them. Uh, it also has a sum of the masses term in there. So once you figure out what that period is, you can use that to help you determine the sum of the masses. But you can also use the fact that this radius, notice I'm just pointing to the diameter from star two position all the way to the opposite side. That diameter, or half of that radius, is way smaller for the massive star than it is for the low mass star. So that ratio gives you a ratio, the ratio of the radiuses gives you the ratio of the masses as well. So that's two equations, two unknowns, and you can actually solve it and find the mass of not only one star, but both of the stars. And once we started doing that, then we could quickly discover the masses of stars. And that allowed us to realize the role that mass actually plays in the brightness, lifetime, luminosity of a star. Does that make sense to everyone? I'm sorry I keep yawning. I've not been able to sleep very well lately. I've only been getting a couple hours of sleep each night. So I apologize for yawning. Does anybody have any questions about that? You don't have to do this math. Your book shows you how, and that means various courses around the country do make their students do that. I don't make you guys do that, but I want you to understand that this is how mass is found. Once we found that mass predicted how temperatures are and how radiuses are and their lifetime and all that stuff, then you don't necessarily have to be able to figure out the mass of every star. You can just find properties of the star that can allow you to figure out its mass. So that's kind of nice, and that's where the Hertzsprung-Russell diagram comes in. Uh, oh, by the way, the velocities, since the velocity has to be 2 pi r over the period, and this velocity has to be 2 pi big R over the period, and the periods are equal, you can see there's also a relationship between the velocities that's related to mass. So that's another equation you could use as opposed to Kepler's third law. Uh, the Kepler's third law, as you can tell, gets complicated because clearly when you're looking at this star and this star, they both have the same period. So part of Kepler's third law is unambiguous, but the other part is, oh, well, wait a second, what do we actually use as the semi-major axis? Do we use the one for the big star? Do we use the one for the small star? Or do we use some kind of average? We know how to do that, by the way. It's just a matter of that's not easy for you guys to wield. So it's better for us to use the equation relating the velocities and the equation relating the radiuses of the orbits, and then solve that system with two equations, two unknowns. So by doing this, after we surveyed all the stars that we could see, and we continue to survey all the stars that we see, we try to get as much information about every one of those stars as we can. We try to get their temperature, we try to get their mass, we try to get their distance, and we know their brightness, so we can then use their distance to get the luminosity, all that good stuff we try. After all that analysis is done, what we discover is the lowest mass stars are about 8% of the mass of the sun, which, if I remember correctly, is like 60 times the mass of Jupiter. So if Jupiter had been 60 times heavier, it would have been an actual star. What we do find is that is consistent with our models of how stars form. We actually predict a certain critical mass at which a star can fuse hydrogen and helium, and we get essentially 0.08 solar masses. And lo and behold, when we looked at stars all over the universe, everywhere we can see them, most of which, of course, we see right inside of our solar system, or excuse me, inside of our Milky Way, then we find that the smallest is about 0.08 solar masses. Our models also predict that the largest stable star should be around 150 solar masses, and that's generally the biggest stars we find. But to date, as of 3 years ago, I read that they found one star whose mass was like 156 or 170 solar masses. That's an ongoing discussion. People are trying to figure out how a star could actually be that big. So that might be some new science coming down the pipe soon. It might actually be solved. I don't get access to journals, and if I did, I probably wouldn't read them all. Wouldn't have the time. But either way, that is ongoing science, so that's interesting. Here's where they're showing basically the observations for two stars in orbit. If we're lucky enough to have them be in the same plane that we're in, then we can get spectral lines for star 2 to shift left and right, while spectral lines for star 1 are shifting left and right. But notice at any given time, the shift will be the opposite. So star 1 at any given time will be going the opposite direction of star 2. And if we get them when they're actually both parallel to their center of mass, or excuse me, their center of mass line that goes from their centers to the center of mass, when that's perpendicular to us, then we'll get the maximum velocity of star 1 as it's going away from us and therefore is redshifted, and the maximum velocity of star 2 as going towards us, which is blue shifted. And we can use that redshift and blue shift to calculate the actual velocities. Once we have the velocities, we know that obviously the velocity of star 2 is going to be larger than the velocity of star 1. And what we'd say is that velocity is directly proportional to mass. So big mass means big velocity, small mass means small velocity. So you can literally say V over M is equal to a constant, and then that's true for the other one as well. So we say V1 over M1 equals V2 over M2, or you can ultimately say V1 over V2 is equal to M1 over M2. That's one of the equations. Now, if it's on, uh, in the plane as us, then we can also tell how far these two are apart from each other and how far they are from the center of mass just by watching them. And when we make a plot of their Doppler shift like this gives us our max velocity, which we can write with that V1 over V2 equals M1 over M2. And if we use the size on the actual screen of the telescope, then we can figure out how big the orbit is. And that allows us to implement the second equation. So, for instance, a lot of people don't know this, but Alpha Centauri, the nearest star to us other than our sun, is actually not a single star. In fact, it's a visual binary. So, when you look at Alpha Centauri, you can actually see a little companion next to it. The same thing is true with Sirius. The same thing is true with Mizar. Remember, Mizar is the bend in the handle of the Big Dipper. That one's actually, if I remember correctly, there's 5 stars there. So, that's really cool. But anyways, these visual binaries, you can actually see them. The spectroscopic binaries, on the other hand, are too far away to distinguish, but you can still see the pairs of Doppler shifted lines, and that makes it a spectroscopic binary. So if you look at the actual brightness of the stars, even if they're too close to each other, what you'll see is basically a certain level of brightness all the time. But when one star eclipses the other, you lose some of the brightness. So what we're suggesting here is you're losing a little bit of brightness with this little star in front of this big star. Okay, I'm talking about radius here, and I'm assuming it's, this is a scale drawing. So what's happened here is this little star, which actually puts out its own light, okay, it is still putting out its own light, but it's also blocking a part of the bigger star's light. And that's why we get a little dip right here where this star is going in front of it. Then once this star gets, say, right here or right here, then you're getting the full brightness of the little star and the big star. So we get this line. But when this star goes behind the bigger star, we see, oh, this little star, which is blue, must be way more luminous than the reddish star, because when it goes behind the star, look how big the drop in intensity is. Okay. But when it happens again, when we get back to the little star, the little dip, then we know the period of the orbit. The period of the orbit is from here to here. So 2 identical parts of the graph. So this part where it first drops down, that could be it. The center of it, where it first, where the dead center is to the center, is another way of looking at the period. Or the end of it to the end of it is another way of looking at the period. But with an eclipsing binary, that's how you can actually get basically the period of the orbit, which, like I said, the period of the orbit can help us between Kepler's third law and the other information, the 2 pi r over t. You can also measure the radii of these stars. So once you have an idea about the temperature, which is pretty easy to get, as I've shown you 2 different ways, you can start to work out roughly how much luminosity comes from each one. And from that, you can actually determine their radius, because in order to block this much light from that orange star, you have to account for X percentage of that orange star's disk being covered. That X percentage happens to be pi r squared over pi r squared of the big star behind it. So that allows you to determine the radius of the 2 stars. Now, when all this was said and done, we found that it was really super convenient to make a plot of luminosity, or you can also say absolute value, absolute magnitude, visual magnitude, on the vertical axis. And then you can plot temperature, spectral class, or even wavelength on the horizontal. So when you do that, notice that there's a relationship between wavelength and temperature and spectral class. That's why you're doing all of them at once. Just like there's a relationship between luminosity and absolute magnitude, that's why you can do them all at once. When this graph was made, it was discovered, something really big was discovered, and that is the vast majority of stars that are low luminosity actually have very low temperature, and the vast majority of stars that have high luminosity have a high temperature, so they're over at this side. And as you go to lower and lower temperatures, the luminosity falls lower and lower. That's the norm, and this is the main sequence. This is that classification V that I told you about. Anything that appears on this line is called the main sequence. And this might look a little abstract to you, but it's the same thing as if you plotted, let's say, horsepower on the vertical axis versus mass on the horizontal axis. Okay. So if you talk about horsepower of a car, you would expect very light cars, let's say these over here, to have very little horsepower, like a Honda Prism, or excuse me, a Toyota Prism, or let's say a Honda Prius. Is that a Honda? I can't remember. Anyways, the electric cars and stuff like that, the Pulse and those sort of things, those are very light, and you expect them to have very little horsepower because their whole intent is not to be powerful, but to be economic. So you'd expect their masses to be low and their horsepower to be low. And then you expect, say, a F-350 or a Chevy 3500. You expect that vehicle to be quite heavy. And in fact, because it's so heavy, you need it to have a big horsepower or a lot of horsepower. So that explains the ends. And then you'd explain, okay, well, what about a Lincoln Continental? Well, a Lincoln Continental, which used to be police cars, or Crown Victorias, which also used to be police cars, those things being kind of big, but not as big as a truck, still need a little bit more horsepower than, say, the Nova. So you'd have over here a slightly higher than average mass, would have a slightly higher than average horsepower. And the same thing with a slightly lower than average mass would have a slightly lower than average horsepower. Now, then you have the extremes, and the extremes would be things that are super, super light, which would be this end, but have a buttload of horsepower. So that would be your dragsters, your funny cars, your race cars. They would all be over here. And then you'd have these other things that are hugely heavy, but in fact have some low horsepower. And that might be like your earth movers. Like those, I don't know if you've ever seen those dump trucks that they use around mines where the tires are like 7 feet tall and the trucks are like 30 feet tall. Those things don't necessarily have a huge amount of horsepower, but they do have a huge amount of weight, and they would be over here. In this diagram, where we're not doing horsepower versus mass, we're doing luminosity versus temperature, and notice the temperature goes up from right to left, just like the mass went up from right to left. So it's opposite of what you're experiencing. But because of that, the actual temperature goes up. It's the wavelength that's actually going down from right to left, but the temperature is actually going up, from right to left. Okay. It's the wavelength that's doing the regular thing. So over here, low luminosity and low mass is actually, or excuse me, low luminosity and high temperature is actually the white dwarf. So this is the area that you call WD. This is the area you'd call V for main sequence. And then, of course, up here you've got giants and supergiants and subgiants, and those are where the I, and III, and IV come through. Now, here's the cool thing about this. So this Hertzsprung-Russell diagram is monumental. This little line right here basically says, hey, the equations that must be met for a star to be stable are being satisfied by a very select few, and that select few are the ones that can actually find their luminosity versus temperature relationship along this line. Once those equations start to be violated, which basically starts to occur when you're running out of hydrogen to burn in the core, then they leave this main sequence and go to these other things. In fact, they'll go off this way, and sometimes they'll zig and zag back and forth, and then ultimately end up way back here. But by doing that, we've managed to put not only these things on this line, but we've put them this way in a very specific order so that we know that this end is the 0.08 solar masses, and this end is the 150 solar masses, and this spot right here is exactly one solar mass. So you can actually, by classifying this as a main sequence star, and there's ways you can literally look at the spectrum and tell it's a main sequence star. So if you just plot the temperature of a main sequence star, boom, you automatically get the luminosity. Or if you are just plot the luminosity of the star, then boom, a main sequence star, then boom, you automatically have the temperature. But it's actually harder to do the luminosity than it is the temperature. So we normally just take a temperature, and if we know that the spectra shows the spectra of a main sequence, then we know we go up from the temperature until it hits the main sequence line. That gives us, yes, the luminosity, but it also gives us the mass because, like I said, as you follow this line along, it goes from 0.08 solar masses to one solar mass to 10 solar mass to 100 solar mass to 150 solar mass. So you get the mass out of an exchange. If you use the Stefan Boltzmann law, you can actually also plot out the lines of constant radius. And it turns out that this is about a thousandth of the mass of the sun. This is about a hundredth of the mass of the sun. So anything along this size will be 1/100th the mass of the sun along this line. I mean, anything along this line will be 1/10 the mass of the sun. Anything along this will be exactly one times the mass of the sun, 10 times, 100 times, 1,000 times, 10,000 times, so on and so forth. And that's about as big as we get. So by plotting these things, we automatically get to find out cool stuff. We find out the radius, we find out if it's on the main sequence, we can find out the actual mass and therefore the lifetime. And from temperature, we just got all that stuff for free. So everybody see the usefulness of this Hertzsprung-Russell diagram? Notice it is weird. The highest temperatures on the left. This is like starting the origin at x equal infinity and running it off to x equals 0. That's really crazy, right? But that's the way they did it. And you can imagine why, because remember, Wien's law says the temperature is inversely related to the wavelength. So this is really an increasing wavelength graph that it is. Increasing wavelength, of course, means decreasing temperature. When we did that with clusters of stars. Remember, clusters of stars are all born sort of in the same nebular cloud. And basically, when one lights up, the others light up. In other words, when one is created, that has a thermonuclear explosion, the helium flash type thing, or actually it's a hydrogen flash in this case. And that's sort of like detonating a nuclear bomb. It sends off a pressure wave, and that could actually create other stars or help other stars become protostars, become stars. So they all basically were born about the same time, and they're all basically about the same distance away, because usually the size of a nebular cloud is small compared to the distance it is away from us. So when we actually plot all the stars that we can find in a cluster of stars, we'll have stars from 0.08 solar masses all the way up to 150 solar masses, and we'll plot all those. And when we do that, what we see is, depending on the age of that cluster, the stars will start to peel off of the main sequence, leaving the main sequence, going to the giant branch or to the subgiant branch, depending on how much mass the particular star has and how much, what the age of the cluster is. By doing that with various clusters, we could see what masses pulled off at what time. So we'd see 10 to the, 150 solar masses would peel off first, and then say 100 solar masses would peel off next, and then 10 solar masses, and then one solar mass, and then a half a solar mass, and then 1/10 of a solar mass, and 1/100th of a solar mass, and 1/1000th. That allowed us to confirm that, in fact, higher mass stars live for shorter periods of time. And combining that with our models, we could make sense of, say, one particular time period for a particular mass, how many years that should be. And if we're right, then the rest of the years should come out to be consistent with our models. And that's what we found out. So that's how we ultimately got, with a little bit more than 400 years of observation, that's how we were able to put together that stars live at least millions of years old if they're, 100 solar masses, but can live, in fact, trillions of years old if they're around 0.08 solar masses. Okay. In this particular cluster of stars, you can see, in fact, earlier this branch started to leave the main sequence, and that branch went through the giant branch and then came out over here on the white dwarf side. But this later branch started to break off, and that one hasn't gotten as far as the white dwarf. It's actually going along the giant branch. Maybe later it'll back up. Okay. I think I covered everything. Most stars exist on the main sequence. That I've mentioned that it runs luminous hot in the upper left corner to the lower luminosity cool stars in the right corner. Massive main sequence stars are large, luminous, and hot. The key thing is a main sequence star is burning hydrogen at its core. Okay, once that stops burning hydrogen at its core, then it's no longer in its main sequence. It's starting to fall off of this main sequence line and go through various other stages. Okay, that's what we call the end of the death of the star, and it actually happens really quickly. So, if this whole star takes 10 billion years, it's going to spend less than 10% as a protostar plus as a post main sequence star. So that whole time period building up to a star from a protostar and then building to other things after a main sequence star, that accounts for less than 10% of the total star's life, the star's total life. Stars are on the main sequence as long as they burn hydrogen and helium, and the sun is on the main sequence, as we said there. Here it is showing the calibration of the actual masses 0.2, 0.6, 0.8, 1, 1.52. So, like I said, just knowing that the star is a main sequence star, which you can tell by the lines in the spectra. If the lines are really, really crisp, you know it's a really low density thing. So it's likely to be a supergiant. If they're kind of modeled, you know, kind of wide and stuff like that, you can tell usually that within certain reason that that'll actually be a main sequence star. So if you found a star that you've identified by the line widths and stuff like that, that it's a main sequence star, once you know its temperature, all you have to do is make its temperature vertically above. If it's 10,000 Kelvin, I go vertically above and find the spot on the main sequence that corresponds to 10,000, and boom, I put a dot there. Now I have the temperature. I have that it's 3 solar masses. I have that it's almost 100 times the luminosity of the sun. So maybe it's 80 or 90 solar lumens. I also have, by these dates, I can actually figure out how long the star will live. I can tell that it's somewhere between 1 solar mass and 10 solar masses. Here it looks like it should be maybe 5 solar masses, or excuse me, 5 solar radii. So I can even tell the radius of it now. So just by knowing the temperature and recognizing that it's a main sequence star, I get out of that the mass, the lifetime, the radius, and the luminosity. Then I could even use that luminosity to find distance. So that gives me another tool in my toolbox to find distance. But notice it's hinging on our knowledge of the stars. So it's not a pure uh, measurement, if you will. So knowing a star's spectral type and position on the Hertzsprung-Russell diagram allows you to know its luminosity and find its distance. So remember in the distance ladder that I showed you before, I talked about spectroscopic parallax, and I didn't give you any details. That's why you needed to know the Hertzsprung-Russell diagram first. So this is spectroscopic parallax. Basically, once you find the temperature and its spectral type, you can put it on the Hertzsprung-Russell diagram. That will spit out its luminosity. Now you have luminosity and brightness, so you can use that to solve for the distance the star is away. Okay. But by seeing these stars along here and seeing clusters peel off in this order from top left to bottom right, tells us that the highest mass stars live the shortest, the lowest mass stars live the longest, and actually gives us mathematical values to figure that out. So we also get to know how long a star will live. Not all stars are on the main sequence. Here's those other categories I told you about. So you can see 1A is the supergiants. I think 1B is the giants. Excuse me. No, 3 is the giants. Maybe 1A is I forget. But the main thing is 1 is a type of giant, 2 is a type of giant, 3 is a type of giant, 4 is a subgiant. So this line right here is the subgiant. This line right here is the giants. This line right here is class 2 giants. This is class 1B giant, and this is class 1A supergiant. So those are how you classify stars. You can say a star is a F4 1B if you wanted to, and that would just say, oh, well, F4, I know F5 is right here. F4 should be a little hotter, so maybe I go right here. And you could actually, these are actual real graphs, so you could actually measure the proper value of the temperature. And I'm going to run up until I hit 1B, boom. Now I know I don't get the mass because it's not a main sequence star, but I can get a rough estimate of what its luminosity is. I can certainly get a good estimate of what its radius is because the radius lines are like this. So a little bit of motion up and down doesn't cause a huge amount of motion of radius. So I get a ballpark figure for the radius as well. Giants or supergiants are cool, but very luminous. And they're big. Their radius is huge. That's why they're up here in this right corner. Remember, this is the smallest radius, and these are the largest radii out here. So, in taking the measure of the stars, basically, you can have the luminosity and the brightness. And if you have that, then you can get the distance. But if you know the Hertzsprung-Russell diagram, if you just know the temperature, then you can use that to find the luminosity. Okay. And it's really precise if you're doing it for the main sequence. It's a little less precise for those other spectral classes. So, or you remember, spectral classes are the O be a fine girl, kiss me. Luminosity classes are the IV, and V. Okay. So keep those terms in mind, at least for the next test, the test on this chapter. Okay. That's it. We've now completed chapter 13. So that's really all you need to know about in chapter 13. I've covered all the gory details. You can see in the process of science, for instance, that's another good thing to read. And you'll notice that it does include Cecilia Payne right here. She's the one that she's featured as a whole episode of Cosmos, a new series under Neil deGrasse Tyson. It's called, I think it's called Sisters of the Sun. Excuse me. And so in Sisters of the Sun, they basically talk about how she figures out what those spectra are about. And basically figures out that the O be a fine girl, kiss me is related to temperature. She figures out that the lines are about hydrogen, helium, and stuff like that. And she writes a thesis on stellar atmospheres that's used by graduate students for decades as the textbook for learning how stars work. So Cecilia Payne did that. Annie Jump Cannon, like you saw in the 1900s, classified hundreds of thousands of stars. We've got Magnad in here, as well as Henry Norris Russell and Elginard Hertzsprung. So these two guys are the Hertzsprung-Russell diagram people. Basically, what Magnad Saha showed was that the stellar characteristic in question was temperature. Cecilia Payne showed that the stars were mostly composed of hydrogen and helium, and modern astrophysics was born really with these two people. So that's a pretty worthwhile process of science, as all of them are, of course. But let me stop sharing and see if anyone has any questions. Looks like we're good to go. So I will post the document that I'm going to have you guys do for lab this week. I'm going to post it in week 13 in your lab course. For right now, I just want you to be prepared to come back at 1:30. If you don't come back, like I said, it's not that big a deal. You're just going to lose your attendance points for today. And other than that, you're free to go. If you have questions, wait, and I'll wait till the last person to leave.
Have a good day.
You too, Amy. Amanda, Jonathan, Matthew, y'all have questions? Matthew normally has some questions.
I don't.
Okay. Well, y'all have a good one, folks.
Thank you.